Hello and welcome again. Today I want to speak to you about formal charge and resonance. So let's move in and take a closer look. These two concepts, formal charge and resonance, arise because the rules of VSEPR have to be modified to cater for certain types of structures that can exist. Let's take an example. The molecule of nitric acid, which is made up of hydrogen, nitrogen, and oxygen, HNO3. Nitrogen has 5 valence electrons, oxygen 6, hydrogen 1. 3 oxygens would mean 18, 1 nitrogen would mean 5, 1 hydrogen giving us a total of 24 valence electrons. When divided by 2, it means we have to have in the structure 12 pairs of electrons. So let's look at a couple of structures for nitric acid. Let's try this structure right here. Nitrogen in the middle with oxygen, another hydrogen, a double bond here to an oxygen, a single bond here to an oxygen. Now let's put in the lone pairs. 2, 4 electrons, 6 electrons here, 2, 4 electrons here, 2, 4 electrons here. If you count, you'll see that you have here 24 electrons in that structure. Let's draw another structure. This one's kind of almost identical to that other one there, but here we'll put the double bond over on this side. And we'll put the single bond down here. Put an oxygen there, hydrogen here. Put in the lone pairs. Here we'll see that, again, we have 24 valence electrons. Now there's a third possible structure that we can have, and that structure looks like this. We put the nitrogen here and the double bond over on this side with a single bond this way. And single bond this way, a single bond this way, 2, 4, 6, 2, 4, 6. If you count the number of electrons, you'll see it comes to 24. So then, how can we decide which of these 3 structures is the actual Lewis structure of nitric acid? And to do that, we must use the idea of formal charge, which works like this. Fc, or formal charge, is equal to the number of valence electrons minus the number of non-bonding electrons minus half the number of bonding electrons. So let's apply that formula to each of the atoms in here. And if we do that, you will see that in this third molecule down here, you get values of -1, -1, and +1 for each of the oxygens. Just try this one here that says +1. The number of valence electrons is 6, minus the non-bonding electrons, 2, minus half the number of bonding electrons, which is 246 divided by 2, 3, and that answer comes to +1. If you do that for these 2 oxygens though, the answer would come to 0. Just give it a try for this one right here. It would be 6 minus 4 minus half of 4, which is 2, comes to 0. And you can work out all of the others. What you'll find is that for this one down below, you don't get any zeros. And the biggest number is +1 and the smallest number is -1, giving you a big fluctuation of 2 units between the biggest number and the smallest number. Whereas over on these 2 structures here, you'll get a 0 and you'll get a -1 up here. Let's take this one right here. It will be 6 minus 6 minus half of 2, which is 1, comes to -1. So that means that these 2 structures will be the favored structures. This one here, which we can call A, this one, which we can call B. Both of them would actually have the identical formal charges. So therefore, we've eliminated the third structure based on formal charge. But we end up with two other structures which seem identical to each other in terms of formal charge. And they are identical to each other, and we cannot distinguish between them. So then, following the rules of VSEPR, we will put that double-headed arrow, and we will say that the structure of nitric acid exists as a pair of resonance hybrids. The term hybrids doesn't always have to be included, but it actually is a useful word to add to it because it removes any misconception that the structure of nitric acid is continuously fluctuating between two extremes, which is a misconception that some people have. The truth is, the bond lengths and strengths in nitric acid, which if we were to redraw it right here, N single bonded to oxygen, here, double bonded over here, and single bonded over here. The actual bonds in nitrogen, between nitrogen and oxygen, are equal to 1.5 in both strength and length. There are 3 bonds and 2 domains, 1, 2. So the bond order here is actually 1.5 as well. Bond order being the number of bonds divided by the number of domains. 2 domains, 3 bonds. And the true structure then of nitric acid would actually look like this, with what we would have to refer to as a 1.5 bond. And the electrons which actually, according to VSEPR, would belong to a double bond, are actually delocalized over the space between the 2 oxygen atoms. But the rules of VSEPR does not allow us to have a 1.5 bond. So therefore, when such a situation arises where you have 2 or more possible valid Lewis structures, then we say we have resonance or resonance hybrids. It is purely a theoretical explanation because VSEPR does not allow us to have 1.5. So therefore, if we were to be sticking with VSEPR rules, which we are, then nitric acid has to be represented this way, that's on the screen. But the true structure of it, if we could go outside of those rules, would be to say that it has a 1.5 bond, which would be represented like this. It would be false to say that the structure fluctuates or resonates between 2 extremes, because all experimental data shows that bond length and strength is consistently equal to 1.5.